Welcome to the Ex Terra Podcast. The Ex Terra mission is to explore and discuss the business of space and its effect on the national and global economy, as well as life on Earth. How does what happens in space affect your life every day? That's what we're exploring on the Ex Terra website, as well as on this podcast. And joining me today is Stefan Powell, CEO of Dawn Aerospace. Stefan, welcome to the program.
Thanks for having me on, Tom.
It's my pleasure. We have been looking at your company off and on, and this whole concept of a space plane is very intriguing to us, and I'm sure will be to the audience as well. But I want to start out just talking a little bit about Dawn Aerospace and what it does.
Yeah, Dawn Aerospace is a space transportation company. For us, we kind of split that into two main things. It's about getting things from Earth up into space, and then from space to everywhere else. You know, they're quite different problems, they're quite different technologies, but we see huge synergies in bringing these two solutions together. You know, when you consider both, you can come up with much better overall ways of doing things. And it also means you can provide an end-to-end solution, transportation solution for your customers, right from starting on Earth to getting them in space to moving them around, doing their constellation management, whatever it may be, and also deorbiting at the end of life. It's all important.
You're taking a kind of a novel approach to getting things into orbit, and I want to talk with you about the Aurora 2, the Mark II Aurora space plane that you've been flight testing. You've done some atmospheric tests, some successful ground tests of the rocket engine. Have you scheduled that first rocket test flight yet, and what are you going to be looking for?
Yeah, I mean, scheduling is always it's a tricky subject when you're talking about R&D projects, especially a space plane is something that, at least the way we're doing it, no one's really done this before. So scheduling, yes, it's sort of in early next year. We're currently putting the rocket engine into the aircraft. We'll be doing all up system tests sort of end of this year, early next year. And then, we'll be going out and flight testing it.
What made you think about a space plane as opposed to a traditional vertical launch situation?
Yeah, that's a good question and very valid, because it's a pretty different approach, especially when you consider that we're really trying to build an aircraft with the performance of a rocket, as opposed to most other companies are saying, well, let's take a rocket and make it more reusable. And so that they're kind of working from the other end. The way we see the problem is it's really a scalability problem. We need to get space access, we don't want 10 times more space access or even 100. We want to be pitching more towards like 1,000 times more access, because we see the opportunities in space are not, they're not going to plateau at 10 times what we're doing now. When you start talking about mining in space and energy generation in space, manufacturing in space, even huge amounts of transportation between Earth and moon bases or Mars bases. If you start talking about this really far out stuff, you start wanting to have solutions that can have 100 or 1,000 times more capability to space. And so a vertical takeoff, vertical landing rocket has some pretty inherent disadvantages. And we struggle to believe that these concepts are really going to scale that well, to these very, very far out numbers. But fortunately, there are industries that do dramatically more transportation than space. We do more flights in 2 hours of regular aircraft. Commercial aviation does more flights in 2 hours than the entire space industry has ever done in the last 70 odd years. So clearly, this is a very scalable concept. We understand there are significant differences between space technology and airlines, but we want to bring this philosophy, the ethos, the business models, the general operational concepts, bring as much of that across into space. And we think that we can actually build, certainly the booster, we can really operate like an aircraft. That's the mission of the Mark II Aurora, is to show that we can operate the booster stage really as an aircraft that takes off and lands from an airport. It'll, when it comes back, you can put more gas in it and fly again. It flies under aircraft law, all those good things, all those things that really make it truly rapidly reusable, like you think of your car or a plane being reusable, not refurbishable, like the space shuttle,
right,
or even a Falcon 9 booster. It's refurbishable, but it's not reusable in the same way your car is.
What are some of the unique challenges for getting what is essentially an airplane into orbit?
Yeah, so just to be clear, we don't, at least not yet, we don't intend to get the aircraft stage into orbit. That's significantly more difficult. It's still a two-stage to orbit concept, where the first stage is really that aircraft portion. But still very significant challenges, particularly in terms of like certification. We want to fly as an aircraft. We want to fly out of airports, like I said. So we need to talk to regulators. They need to be comfortable with that. We don't want to have exclusive airspace. That's one of the key things. If you imagine we want to do 1,000 times more flights out of Florida, what's that going to mean in terms of aircraft trying to land at Fort Lauderdale or whatever? That's going to be really challenging. There's going to be a lot of airlines that are not very stoked with you. So we need to integrate with other airspace users. So that's one of the problems that we're already approaching. We can approach that at the subscale as well. That's that problem is, if we're trying to fly to space twice in a day with a subscale vehicle, that problem is basically identical to any scale. So we can show that we can get around these things. We can work with regulators. We can get a license to fly as much as we want. And we can do it safely and cost effectively.
When you talk about certification, and I spent a long time in the aviation business, and certification of an airplane is one of those things that is really a big challenge for somebody who's just trying to build a new airplane. And you're working on kind of a very different concept here. And then you've got to deal with, I'm sure where you are, New Zealand regulations. You have an office in Europe, so you've got the EASA regulations and the FAA. How are you working on certifying this aircraft to be able to operate in all of those different airspaces under those different regulatory structures?
Yeah, super good question, and very difficult to do long term for sure. But we do have a plan for this. So starting in New Zealand is really the key to that question. New Zealand is it's quite a different regulatory regime than EASA or FAA. It's much more. It's much easier to go to government agencies and work with them and actually figure out how are we from fundamentals going to not increase the danger to people on the ground. So this is obviously a very different concept. It's not something they're particularly familiar with, a rocket-powered unmanned aircraft. So the New Zealand regulatory regime has allowances for very unique types of aircraft. There's a Part 102, it's called. Allows you to submit almost any aircraft type and argue from fundamentals why you're able to fly this aircraft. If we were trying to certify this aircraft under Part 23 or Part 25 or something, it just doesn't fit the mold. There's rules in there about how your jet engines have to be designed, and then you say, well, we don't have jet engines. They go, well,
so what are you using? Well, it's a rocket. Well, now we've got a different problem.
Exactly. So once we've established compliance in New Zealand, there are recognized mechanisms for transferring that compliance to other regimes, FAA, EASA, CASA, what have you. So there are established pipelines to do that. But for sure, that's a challenge, probably 5 or maybe even 10 years away for us. We're happy just establishing compliance in New Zealand, and we can do our R&D testing out of here. And likely there's some interim steps flying in places like the USA. There are actually established spaceports where, in the meantime, we can operate out of these spaceports before we really want to scale to other airports.
I would recommend Cecil Spaceport, which is just right outside Jacksonville, where I live. You can just come right here, and we're all set up for you, ready to go. So
perfect. Happy. That's Florida covered. Then we've got agreements with Spaceport America, Spaceport Colorado already. There's good coverage in the States.
When you look at, I think this is an interesting concept, because I wasn't aware that you're going from the ground with a rocket engine. I guess, assumed that you'd have a jet engine to get the airplane off the ground and to altitude, and then the rocket engine would take over. But this is something that's going to start as a rocket and end as a rocket. Does it glide back like a shuttle does, or does it come back under power?
Yeah, it glides back. So that's the real advantage. Being able to burn all of your propellant on the ascent means that you come back, light as a feather. You've dropped nearly 80% of your mass on the way up. So your wing loading and everything is super light because you've got no fuel on board. That means all your dynamic pressures, all the aerodynamics coming back are not nearly as challenging as what you would otherwise think, especially because our wings were large enough to take off. That means our wings, our wing loading is much, much lighter than something like the space shuttle. The space shuttle was really it was a controlled brick really on re-entry. Our vehicle comes back much more like a leaf. And so the aerodynamic environment is much, much less challenging than, say, for a space shuttle, for sure, because that came back from orbit as well. And also much less challenging than like a Falcon 9 boost or an Electron stage. They come back, I think their maximum Mach numbers get well above 5, sometimes in excess of 8 or 9. And our maximum Mach number will be in the low 3s. So, these are not similar regimes. It makes our life much easier.
I have tried to fly the space shuttle landing simulator down at the Kennedy Space Center for the landing, and I have yet not crashed it. So I've got a lot of respect for those guys. Give us a little bit about your background, Stefan, and talk about your team just a little bit.
Yeah, my background, I studied aerospace engineering in the Netherlands and did a master's in space systems engineering, so pretty classic there, I suppose. I had exposure to some interesting startup companies as well, Rocket Lab in the very early days, as well as some other satellite component companies in the Netherlands. The team is generally, a reasonably diverse bunch of engineers from both New Zealand and Europe. We draw a lot on the European sort of deep space expertise there. That's really key. We like to pair that with the slightly different mentality and skill set of our New Zealand engineers. Roughly speaking, New Zealand is very good at doing early stage R&D, figuring out different really difficult problems and being very pragmatic. That comes from being quite a young nation in our own right. While the Netherlands really has this sort of deep experience in space. They've been doing it just about as long as any. So combining these two mentalities, these two cultures, means we can kind of get the best of both worlds, and then also combined with the deep customer base, funding streams and whatnot in Europe, through European Commission and ESA. Combine that with the New Zealand regulatory regime, open skies, all that good stuff.
Right.
We can kind of get the best of both worlds. Yeah.
When we talked about the regulatory things and we talked about certifying the airplane, but there's also, at least here for the FAA, an Office of Space Commerce that deals with licensing launches and recoveries and those things. Are there different regulatory considerations for operating a space plane as there are for a rocket?
Yeah, it kind of really just depends how you want to treat it. And I wouldn't say I'm yet an expert in how the US treats that.
I don't know that anybody is.
yeah. Well, this is also part of the problem. We're pushing the boundaries on how people think about these things. One of the key boundaries in New Zealand is, okay, we want to operate the vehicle as an aircraft, so it's going to get an aircraft license to be able to, all of its flying that it does under 60,000 feet is all jurisdiction of the Civil Aviation Authority in New Zealand. So, okay, we need a piece of paper from them that says we can fly. But once we're above 60,000 feet, they say, look, we don't care anymore until you come back. But you are in somebody else's jurisdiction. So, now we need to talk to the New Zealand Space Agency and get a high altitude license. And if we're putting something into orbit, then we need, a license for that too. So we work very closely with these agencies to figure out scalable, useful ways of licensing this stuff. They're not in the business of trying to make this harder than it really is. They can see they can see what we're trying to do, and they want to come up with scalable ways of licensing this that we can get, licenses for an envelope, that we, that's a blanket license that we can operate under the same way that you operate an aircraft.
And that was one of the issues that came up with a recent Virgin Galactic flight as well, because they got outside their envelope and wound up having to have some lengthy conversations with the FAA about that.
Yeah, for sure. That's you don't want to do that.
So take us through just a typical Aurora Mark II or Mark II Aurora mission profile.
Yep. So that's the operation teams, they drive out to the launch site. They've got everything packed up in a trailer, and takes them a few hours to set up. That's all the radio gear and ground support systems and stuff. Then the aircraft gets prepared in a few hours. Gets fueled up, and then they pretty much push it out onto the runway. Or they see what's going on in terms of the local airspace. A NOTAM goes out to notify other air users that will be operating in the area. And then we're basically free to operate. So we use storable propellant, so we're not particularly time bound. We're not like constrained by liquid oxygen or something boiling off. We'll have hydrogen peroxide and kerosene. So pretty much when we're ready, we're able to start up the engines. We take off in about 2 or 3 seconds. We rotate, pull up, and that is almost the major function of it as an aircraft. Once you're through that, you're into a high angle climb. Somewhere between 70 and 85 degrees most of the time. And you keep accelerating away until I believe engine burnout is something in the order of about 45 or 50 k's altitude. And then it coasts up to above 100 kilometers altitude. During that non-aerodynamic portion of flight, which is anything above 30-ish kilometers, 100 and something thousand feet, you don't really have aerodynamic control anymore. The vehicle is controlled by a reaction control system, also powered by hydrogen peroxide, much like the X-15 was. That controls all your re-entry angles. You're now reasonably far downrange, on re-entry. Peak velocities or peak Mach numbers are about 3.1, 3.2. We re-enter at about 20, you really start to hit the atmosphere at about 30 kilometers again. And I believe the bottom of our pull-up is about 25 kilometers. So, still quite high. The atmosphere is still very thin at 25 kilometers. You're pretty much just doing a max G pull-up at that point, which is really quite high because you're super light. We have to design the aircraft to survive several G at maximum takeoff weight. So when you burn 80% of your propellant, 2G of your original weight is now, more like 10G. So you can do a 10G pull-up on your re-entry, and then just continue to scrub all your energy in the high atmosphere. And once we're happy with the aircraft in that upper atmosphere, we turn around and start gliding back home. And that's all the subsonic glide back home, and we're able to control the energy using split rudders and things like gear timing and just the general, by controlling the elevator of the aircraft, we can pretty much time just control our energy on that descent and stick a landing just like a shuttle does.
Is it mostly automated, or do you have a pilot flying it from a remote location?
Yeah, also a very good question, and important for certification once again. From a certification point of view, it's always a piloted vehicle. There is always a pilot in the loop. Now, of course, just like regular aircraft, it's highly automated. There is plenty of computers in the loop helping the pilot, but that's the key point. It's helping the pilot. They are at no point critical. They just really increase your chances of success. So for sure, there's the computer can control just about everything. It can. We're pretty close to being able to do end-to-end flights, fully autonomously with a pilot just standing on standby monitoring things.
I'm talking with Stefan Powell, CEO of Dawn Aerospace, on the Ex Terra Podcast. Take a moment right now to click subscribe to make sure you don't miss any of our podcasts, or if you're watching on YouTube, any of the videos from Ex Terra, the Journal of Space Commerce. Let's shift gears a little bit, Stefan, and talk about your other business, because traditionally a lot of spacecraft have used hydrazine for fuel for their thruster systems, but you have a new green propellant system. Talk with us about that and its advantages over the hydrazine.
Yeah. I believe we were the first company ever to use nitrous oxide and propylene on orbit. So that was a nice small claim to fame. Yeah, it's kind of an interesting propellant in that it's very, very simple and robust. That was one of the key things that we saw. Like, once again, if we're thinking about space at 1,000 times the current scale, what do you need? You need decent performance, simplicity, and scalability. You have to be able to produce heaps of this stuff at low cost, and it needs to just work. Like, it's really simple, to be honest. Right. So getting rid of the toxicity of hydrazine was, the militaries deal with that just fine. Large commercial organizations can do it, but when you want to have hundreds or thousands of different organizations operating satellites, you just got to get way simpler. I couldn't imagine a car running on a fuel that would kill you at 40 parts per million, and vaporizing, you couldn't fuel up your own car at a gas station. So you just run into these really basic practicality things. So, that was a key thing. We wanted customers to be able to fuel up their own satellites. I don't want to be in the business of having to go to launch sites and do that. We do that now, but it's a stepping stone to a much more scalable thing. So nitrous oxide and propylene, it works really well. It's super simple. You don't need pressurant system, helium pressurant systems. You don't need propellant management devices. The tankage becomes way simpler. It becomes way lighter. So the performance is significantly better than hydrazine monoprop. It's a little bit worse than hydrazine biprop. So the performance is super acceptable in that sense. But the cost is just dramatically lower because of how much simpler it is, and how much more available the propellants are. It's not uncommon for users to pay in excess of $500,000 just to fuel a hydrazine system at a launch site. We sell entire systems for less than $100,000, including fueling. So, you can see how, the cost difference is just dramatic, and that really enables customers to do entirely new things in space. It makes them think totally differently about what can I do with propulsion now that I can have, dramatically more of it, or I can afford to put it on satellites that I previously couldn't have. Say, for example, CubeSats. It was almost just unobtainable. You couldn't put chemical propulsion on a small CubeSat because it was just a $2 million mission was going to need $1 million worth of propulsion. Is just silly. So
how does what you're doing compare with the Ascent green propellant that's being developed by the Air Force Research Lab?
Yep. Now, I'm certainly not an expert on Ascent. I've never worked with it myself, but my interpretation of it, and I hope there are other experts out there would correct me if I'm wrong, is that really the intent was as a hydrazine replacement. So it still has a few of the bottlenecks that hydrazine have. So I would say it's reasonably appropriate if you were happy with hydrazine beforehand, but you just don't want the toxicity. There's still a few problems with that that we wanted to design out. So, it still requires catalysts. It still requires a lot of preheating. It's not particularly scalable in that this is a pretty fancy chemical. It's not widely available. It's not widely understood. It's much easier to handle, but it's not as easy to handle as nitrous oxide and propylene. Every hospital in the country has nitrous oxide supply, and just about everyone who's ever used a barbecue would know how to use propylene. It's basically the same as propane. And so, the level of accessibility is not the same. So Ascent does have pretty fantastic performance when it works, but because it uses catalysts, that means it's you eventually kind of ruin these catalysts. It's a life component. If we think of a world where satellites are constantly getting refueled, eventually having a life component like that is pretty problematic. Our engines will keep firing as long as there's gas in the tank. It's like a spark ignited system. So just like a car engine, it'll pretty much keep going.
So why does green matter in space?
It matters on the ground.
Okay.
And all satellites start on the ground. So sure, it's not about carbon emissions or anything in space. For sure that's nonsense. But yeah, toxicity on the ground really matters. There's been several hydrazine spills in the past that have rendered, parts of NASA facilities or large areas extraordinarily toxic or unusable. It's just a really high compliance cost. Like I say, that $500,000 fuel bill, which is not uncommon for a hydrazine system, that's really just derived from that toxicity.
Now, your thrusters have been flown on a number of systems in space, and they're going to be flying in the near future. Talk about the thrusters that you have under development.
Yeah. We're super proud of 33 thrusters on 8 different satellites, many of which are still operating or still doing stuff. The ones that we have in development. So we're certainly still improving the performance of the thrusters that we have. We really wanted to be fast to market, so I wouldn't say that our thrusters are as good as they possibly can be. They're very, very robust, but there are some things about them that could be better. We could have higher combustion efficiency, higher ISP out of them. There's still plenty to squeeze out there. And yeah, we can also make them more compact, lower cost, again. All of these things are kind of iterative improvements, so we're working on that. And the next real big step is to build larger engines as well. So these propellants scale up really well. That's also another problem with like LMP103 or the other ADN-based propellants, is that they've really had problems scaling up. That's actually making larger engines for us is actually easier than small engines. It's really just about being proven in market. It's great to build engines that are appropriate for $200 million satellites, but if you can't convince the people that build $200 million satellites to use your new fandangled technology, it's not much use. So we're starting to get to that stage now where 30 thrusters in space is not heaps, but we should get to sort of 200 or more within the next few years, and then we really have the product and the core technology well enough established that people that build larger satellites, geostationaries, would actually find this technology attractive. So yeah, we're starting to build the larger engines for them, as well for other missions like lunar missions, asteroid missions. There's some stuff we haven't announced there that we've already signed. So cool.
When you start flying the Aurora with a rocket engine, are you going to be using that nitrous and propylene fuel in the spaceplane, or is it a different fuel than you use for the thrusters?
It's actually quite a different technology. So the nitrous oxide and propylene is great for space because it's super robust and super simple. That's what satellites need. But it's not particularly good for a launch vehicle because it's quite high pressure. So it has quite heavy tanks. So we use hydrogen peroxide and kerosene for our space planes. It's pump fed, much better, impulse density. You get a lot of power in a small system. So that really suits aircraft very well.
Talk about the difference between your approach to a horizontal launch and a company like Virgin Orbit.
Yeah, so there's a few different ways you can slice this or think about it. Virgin Orbit, if you took their rocket, if you look at the mass fractions of the rocket itself that they launched, you'll see that the payload fraction of that rocket is worse than a similar sized rocket or even a smaller rocket like Electron. So you can kind of roughly see that actually the air launch factor doesn't add anything to the entire launch vehicle. In fact, it makes it less efficient. So for sure, that the aircraft is providing some delta V. It has speed, it has altitude, that's useful, but it imposes so many other requirements on the vehicle, like aerodynamic and structural, that the entire launch system actually becomes less efficient when, even just in terms of the expendable portion. So for us, it's very different. The expendable portion is just the second stage. That's about 10% of our total hardware. And by doing so, by having the vast majority of the system be reusable, we're actually saving a ton of cost there. So the be all and end all is how much does it cost to get my stuff on orbit? The highly reusable spaceplane concept is much lower cost.
So how is the second stage integrated into the spaceplane?
That's something we haven't talked too much about publicly. We will have some information coming in about that. We have some rather unique concepts for that as well.
Good, we can have you back.
Yeah, exactly. So suffice to say that once again, the key philosophy needs to be maintained, and that it really has to fly like an aircraft. So I don't want to be dropping stuff off. There's no fairings. There's no other deployable things except the second stage and the payload itself.
Do you have a timeline for getting your Mark III variant operational, or is that just still too far out in the future?
Yeah, I mean, we have internal timelines, but I don't think it makes too much sense to talk about them publicly, just because it's highly dependent on how our development with the Mark II goes, how we go raising money. Suffice to say that we don't think we're in a huge hurry. We don't, that this technology will be so transformational that it doesn't really make a huge difference to us as a company of whether it happens in 5 years or 10 years. In saying that, we are pushing forward as fast as we can. We are moving pretty quickly. Once we've proven this technology in the Mark II and completed its mission of flying to space twice in a day, we think we have a very solid footing to go to the world and say, hey, look, we have a truly transformational technology here. It's really just a case of scaling this up. The major hurdles, especially the ones that aren't technology based, like will governments and certification agencies and the general ecosystem let you actually do this? If we've answered that at the subscale, I think it's not trivial, but it's certainly doable. It then just becomes an engineering problem of let's scale this up, let's make a larger vehicle.
And of course, every space company has met all of their timelines just exactly as they laid them out.
Of course. Yeah. I mean, we're just as guilty as everyone else in that respect.
Stefan, we're just about out of time, but I want you to take a moment and look at, if you might, over the next 10 to 15 years as it relates to space commerce, and tell me what you see.
Our core company thesis is we don't know what's coming. We only know that there's a lot of something coming. I don't know if it's going to be manufacturing in space. I don't know if it's going to be energy harvesting. Some of our customers are just doing things you never thought were going to be a thing, like data servers in space, or all kinds of different communications relay networks. One of them is a space entertainment company doing essentially, artificial shooting stars was one of our customers. Our core philosophy is we don't know what's coming, but we know there's a lot of it coming. They're all going to need to get to space, and they're all going to need to move around in space. So as long as we're working on ways of making that easier, more cost effective, and more scalable, we're on the right track.
Well, Stefan, it's been an interesting conversation, and I do hope you'll come back and talk with us again as you continue down this path, and we wish you all the best of luck.
Cool. Thanks for having me on the show, Tom.
Stefan Powell is the CEO of Dawn Aerospace. And that's going to do it for this edition of the Ex Terra Podcast. You can subscribe to the audio version of the podcast on Spotify, Apple Podcasts, and many other popular podcasting platforms. Be sure to click on subscribe so you don't miss an episode of the podcast or any of our other videos. You can also get daily space commerce news at exterrajsc.com. And one thing more, be sure to connect with us on LinkedIn and follow us on Twitter at exterrajsc. Until next time, I'm Tom Patton. Thanks for joining us.